In this simulation, we wanted to model a scenario from something that we both enjoy, that being football. As fans, we're amazed by some of the things that these athletes can do. For example, how far they can throw the ball under pressure or on the move, how fast they can run, and their catching ability. When thinking through our options, it was clear that exploring a two-dimensional kinematics problem under different physical circumstances was the path that we wanted to take to physically explore and visualize the extremes of the different effects on a specific scenario under four different physical scenarios. In this simulation, we model a 53-yard touchdown pass from Patrick Mahomes to Tyreek Hill and their Week 2 matchup against the Chargers. This scenario is particularly fun because Uday happens to be a Chargers fan, and the Chiefs went on to win by 3 in overtime.
Thanks, Brian. Our goal in this experiment was to simulate the scenario as a 2D kinematics problem and analyze the two objects as a collision under different physical scenarios. The different physical topics explored include 2D kinematics, projectile motion, changes in acceleration due to gravity, and air resistance. Our first simulation explores the scene under ideal conditions, meaning no friction, no air resistance, and a gravitational acceleration constant of 9.8 meters per second squared. This allows us to model the scene as if it were in a vacuum and serves as a baseline scenario when comparing it to other scenes. Our second scenario takes place on the moon, where the objects are under the effect of microgravity. The third scenario takes place on Jupiter, where the objects are under the effect of hypergravity. And our fourth scenario introduces air resistance into the mix. Brian, do you want to explain further?
Absolutely. So in order to model our scene, we wanted to represent each object by a specific point particle. The first point particle is for the football thrown by Patrick Mahomes, and it has specific dimensions that we had to account for in this particular circular object. A typical NFL football per regulation weighs approximately 15 ounces, which is 0.4252 kilograms, and is 11 inches along the elongated axis. And that equates to a radius of 0.1397 meters of this specific object. The projectile is launched at a 25-degree angle with the horizontal at a velocity of 60 miles per hour per how fast Patrick Mahomes can throw a football, which is equal to 26.82 meters per second. The larger point particle represents Tyreek Hill with a height of 5 feet 10 inches. And let me find him real quick. There he is. A height of 5 feet 10 inches, or 1.78 meters, and a weight of 185 pounds, which is equal to 83.9146 kilograms for the mass. He moves at a constant velocity of 8.53 meters per second based on his 4.29 second 40-yard dash time. This scenario was analyzed as a collision problem where the football thrown by Patrick Mahomes at the launch angle collides with Tyreek Hill for a touchdown catch. We have modeled each particle or system as a point particle represented by the circle with only translational velocity and their specific dimensions and measurements as we highlighted. So for our ideal condition scenario, the effects of friction and air resistance were ignored. Thus, the only physical property is the acceleration due to gravity, negative 9.8 meters per second squared. We'll analyze the typical projectile motion problem as if it were in a vacuum and see what happens. Here we see the two objects collide, and I'll kick it over to Uday for more observations.
So in the absence of wind resistance, the path of the ball follows a parabola, and we're able to use the constant acceleration equations to determine the ball's velocity and direction in the xy plane. Using these equations, we're able to determine various metrics, such as the minimum distance Tyreek Hill would need to be from Patrick Mahomes when the ball is thrown. The metrics we will be using to compare the effects of gravity are all relevant football metrics used in real games. For this particular scenario, the ball stays in the air for about 2.31 seconds. It travels a distance of 56.23 meters. The distance that Tyreek Hill needs to be from the quarterback when the ball is thrown is about 36.5 meters. And the amount of time that it would take Tyreek Hill to get to that distance from Patrick Mahomes is about 4.28 seconds. So what that effectively means is that Patrick Mahomes would need to be protected for about 4.28 seconds in order to give him enough time to throw the ball, and in order to give Tyreek enough time to get to that particular distance. I'll kick it back to Brian for our second scenario.
So for our second scenario, we will analyze the problem under conditions on the moon, where the acceleration due to gravity is equal to negative 1.62 meters per second squared. It's unrealistic to believe that Mahomes or Tyreek Hill could throw or run at the same relative speed under these conditions, so we have to assume that Patrick Mahomes launches the ball from his prosthetic rocket arm, which happens to be a fair comparison based on the sports media portrayal of him possessing a rocket arm, at the same initial velocity as the previous scenario. We're assuming Tyreek Hill is now positioned in a moon buggy at his same velocity of 8.53 meters per second, and no changes have been made to the specific objects other than highlighting these special circumstances. We'll now analyze the simulation and observe the motion. And I'll zoom out more just so we can see the entirety of it. little bit of following along, as it is a long journey and contact with the ground. And over to Uday for some observations.
So as you can see, in this scenario, we observe the effects of the change in acceleration due to gravity on the moon. To nobody's surprise, we observed a massive change in the projectile's motion in the path of the football. Patrick Mahomes severely overthrew his target with his rocket arm as the total distance covered by his throw was significantly increased from about 56 meters to about 340 meters from the initial starting position. This new distance is almost 4 full football fields. We see that there's no possible way for Tyreek Hill to reach the pass unless he started from a position much further down the field. This position we calculated to be about 220 meters away from Patrick Mahomes' position, which is much, much farther than it would be under ideal conditions or on Earth. More impressively, in order for Tyreek Hill to even get to that starting position, he'd have to run for 25 seconds before the quarterback could even throw the ball. That's a lot of time to protect someone on the football field. The ball itself would stay in the air for an astonishing 13.99 seconds. And if you think about it, in terms of the game of football, that gives cornerbacks and defensive players plenty of time to position themselves in a way to disrupt or intercept the play. Brian, I'll pass it back to you for our third example.
Perfect. Thanks, Uday. In our third scenario, since we had so much fun looking at the previous two and the one on the moon, we thought it'd also be interesting to look at hypergravity and how that would affect the interaction. Here we model the problem on Jupiter, where the gravitational acceleration is negative 24.79 meters per second squared. Again, the same scenario where Tyreek Hill throws and or Tyreek Hill is running from the same position and Patrick Mahomes throws. And now we will observe at a reduced simulation speed so we can see it insert in its entirety. And I'll pass it over to Uday to highlight as we watch.
So in this scenario, we are observing the effects of in this scenario, we are seeing the opposite of the moon scenario as acceleration due to gravity is increased to a value much greater than that of Earth. Because of the significant increase in gravity, we see the ball does not come anywhere near to reaching Tyreek Hill, and thus no catch is made. In this scenario, the wide receiver would have to run a short route like a slant or a corner in order to be close enough so that the ball would actually reach them. As a result, Jupiter football would be some sort of a miniature game, similar to the size of a tennis or volleyball court. Some interesting stats: in order to make this catch, Tyreek Hill would have to have an initial starting position of just 14 meters from Patrick Mahomes. Compared to the 220 meters on the moon, that's just 6% of the distance. It would also take Tyreek Hill just 1.7 seconds to get to his starting position. And that definitely helps out the offensive linemen because they would not have to protect their quarterback for very long before he needed to throw the ball. The ball itself would stay in the air for about 0.9 seconds, which is quite quick. I'll pass it back to Brian for the final scenario.
For our final scenario, air resistance was introduced with a multiplier coefficient here, we will see, of 10. We wanted to have it be an extreme scenario so we could see the absolute effect on the circumstance that it has. We will observe the simulation, and I'll pass it to Uday as we watch to highlight some observations.
So here we observe the effects of air resistance on the model, and you'll see that the path of the ball is no longer a parabola. Rather, it's a deformed parabola. And this is because there is the force of air resistance that is changing the acceleration of the ball as it goes through the air. We looked at some equations provided by NASA on projectiles going through flight without any thrust. And as you can see, there's a significant increase in the amount of complexity that goes into calculating the path of an object that does in fact deal with air resistance. These include variables such as cross-sectional area, density of the fluid, and how velocity or how the force of drag is affected by the actual velocity of the object itself. As a result, you can see how complicated these sorts of scenarios get when you introduce the complexity of air resistance. Overall, out of this project, we found it incredibly interesting to see how different gravitational constants affected projectile motion and gave us quite a view on how astronauts might be able to play football in the future.